Thank you, Ben. I'm delighted to be with you guys and have the opportunity to share with you what we've been doing at Hydro-Québec on greenhouse gases for the last 25 years. So I'm going to give you an overall of what we've been doing in terms of science. Can everybody see that? Ben, you can see the slides?
Yes. Yes.
I'm just trying to switch. It doesn't switch. Okay, there you go. All right. So what we've been doing, it's not a new issue for us, greenhouse gases. We've been documenting that for the last 25 years. We've been measuring greenhouse gases on many reservoirs. You can see on the maps all those dots that are the reservoir and lakes that we've been collecting data for over the last 25 years. We've been measuring CO2, methane, as well as N2O on the surface of those reservoirs with more than 35,000 measurements of CO2, 30,000 on methane, and other aspects that have been measuring as we were collecting information on greenhouse gases. You have to keep in mind that when we started doing the research in early 1990s, we were collecting a couple of hundred measurements a year, and that was a good year. And now we're more on the order of 25,000 measurements per year. As the technology has evolved, we have also changed the way we measure greenhouse gases. So we have more information in the last 10 years than we used to collect the first few years because of technology allowing that. We have two specific projects where we have collected more information. This main one, I'll come back to that a bit later on, where we have a bit more than 250,000 of CO2 measurements. And Raman construction, Raman complex, which is under construction, where we have up to now about 100,000 measurements of CO2, and we're still measuring that over the next couple of years. What we've done in 2002, 2003, it's tried to figure it out. What exactly do we understand of the dynamic of reservoirs in terms of greenhouse gases? And so we work with different universities, 13 universities and research center to produce a synthesis on greenhouse gas emissions. And that's the book, which is that you can see on the right side of the figure. What we've learned from this study or that synthesis, it's that we've looked at natural ecosystems. So how those system works. So you can see my pointer that you have the terrestrial ecosystem that then fix carbon or CO2 coming from the atmosphere as it grow trees or fix carbon for soils and everything. You also have exchange of CO2 from the atmosphere with the water column of the lakes as the wind blows over the lake or the surface of the lake. And part of the carbon that's going to be fixed in the terrestrial ecosystem will reach the aquatic ecosystem, in that case a lake, either through runoff with dissolved or particulate matter in the water, and the water that's going to reach the system. What happens, it's there's more carbon reaching the system of the lake than the inner lake system can fix. So fish food or fish flesh, everything, there's not enough fixation, or the process is slower than the amount of carbon going to the system. So what you end up, it's you have a water system that is super saturated, high concentration of CO2 compared to the atmosphere. And what's going to happen, it's any natural system would try to reach equilibrium. So you have more CO2 in the water than in the air. You basically export or diffuse CO2 from the water to the atmosphere. So that's natural.
Yes. I'm sorry to interrupt. Your audio is a little spotty.
Okay. Is it better that way?
That's better.
Okay, I'm going to keep the microphone close to my mouth. All right. So that's the natural ecosystem. So what's happening when you create a reservoir? Well, you still have the carbon coming from the fixation from atmospheric carbon with the terrestrial ecosystem. You still have exchange of CO2 or methane with the atmosphere at the surface of the reservoir. So carbon coming from the system entering the reservoir, but you have three additional sources of CO2 or carbon in the reservoir that you don't have in the lake. The first one will be related to the drawdown zone, which is the area where the water level will fluctuate as we generate electricity. So with the action of wave and ice, we will erode the small layer of organic carbon or topsoil at the surface of those area. That carbon will go to the water column, and that carbon or organic matter can be used by the biota, bacteria to decompose, which is a natural phenomenon to produce greenhouse gases. The other source that we have in reservoir, it's basically the one that you see here at the bottom. It's the decomposition of a fraction of organic matter present as you create the reservoir. So we're not talking about the trees here. We're talking about the soil layers, the lichens, the leaves of the trees, but the trunk of the trees themselves will remain in the reservoir for a very long period of time, and the order of 1,000 years and go back. So we have two sources within the reservoir, but so more CO2 or carbon going to the water column, and you still have those inputs from the watershed upstream of the reservoir. So you end up with much higher CO2 or methane concentration compared to the lakes, and you have in the same order more fluxes that can be between 5 to 6 times higher than those that you have in the natural lakes. The third sources of CO2 or methane that you have in your reservoir compared to lakes, it's as you regenerate electricity and taking water from the reservoir, we're taking the water deeper in the reservoir, you have water which is super saturated in CO2 or methane. And as it reach downstream of reservoirs, downstream of the generating station, it's you're going to basically the gas CO2 or methane has more CO2 in the water than the atmosphere. So those are the three new sources of CO2 or methane that you have in your new reservoir. But those sources are pretty short in time. They don't last very long. So this is a picture of a reservoir which is older than 10 years. Usually those processes happen quite rapidly. So you still have, after 10 years, the inputs of carbon coming from the watershed or exchange with the atmosphere. Those are still there. But the erosion, the material that could be eroded, because keep in mind that the soil, topsoil and boreal system are no more than 3, 5, 6 inches at the max, at the most. So it's really easy to erode those. So there's no more organic matter in the topsoils of the drawdown area within a period of 3 to 5 years. So no more organic matter, no more CO2 or carbon are produced from those areas. Same thing for the bottom of the reservoir, major part of the reservoir. It's the organic matter that it's easy degradably or easy to degrade, will be used by nutrient by the bacteria production within the period of 5, 6, 7 years. So those two processes or those sources of CO2 or carbon in reservoir no longer emitting greenhouse gases or additioning or adding greenhouse gases to the reservoir after a couple of years, or they are totally absent or really greatly reduced within a period of 5 to 10 years. And as those processes are decreasing over time, then you have concentration in the water that's also decreasing. So the fluxes at the surface of the reservoir is decreasing, as well as the concentration in the water column itself. Therefore, the fluxes downstream is also decreasing within a period of 10 years. What's happening, this is what we call the chronosequence, is basically the emission of CO2 at the surface of the reservoir with the age of the reservoir. The gray area or the blue area, depending on your screen, it's basically the natural values that you observe in lakes or river around Quebec. What you see, it's well known that you have an increase of emissions the first few years between 3 to 6 times what we observe in natural lakes within a period of 10 years. So the impact of flooding is mainly occurring within the first 10 years. The longest in Quebec was 7 years, and the shortest was 3 years. 3 years was East Main, and 7 years was Sainte Marguerite, the North Shore of Quebec. We're still emitting greenhouse gases after 10 years, but those are related to the input of carbon coming from the watershed, as it's the case for any natural lakes or river. So what's happening? What's happening here? It's that we have diffusion. We have 3 pathways, as I mentioned, from emission from reservoir. Diffusion at the surface of the reservoir. This is the most important pathways where greenhouse gases can be emitted in reservoirs. Then you have a bit of bubbling, but these are shallow area. And then you have degassing. And these different pathways can be totally different in warmer area. This is an example from Malaysia. This can change also for Brazil or something like that, but those pathways can change depending of the chemistry or the characteristics of reservoirs. But it can also change a little bit between those three fluxes of pathways in Quebec, but it's mainly dominated by diffusion in all reservoirs in Quebec. So basically what we've learned from synthesizing the information around the world on reservoirs is that natural ecosystems do emit greenhouse gases. The greenhouse gases coming from reservoirs is really related to the decomposition of a fraction of the organic matter flooded by the creation of the reservoirs. And the pathways are the same everywhere in the world. So the quantity of greenhouse gases and the duration and time is really depending where you are, and the warmer is the climate, usually higher are the emissions, and they may last a bit longer over time. But everything we know about burial systems, so Quebec reservoirs, the emission of greenhouse gases decreased rapidly within a period of 10 years. But one thing you have to keep in mind in the synthesis we've done in 2005, 2004, it's really based on gross emission, basically what we measure the surface of the reservoir. So what we've decided to do with the synthesis and following the synthesis is we had an opportunity with East Main 1 reservoir to document the emission from the reservoirs. Then, do you hear me properly? Because I'm not sure.
What's that, Alan?
Can you hear me properly?
Yes.
Okay, thanks. So this is what we've done in East Main 1. It's basically try to understand the net emission. And net emission, or what the ecosystem is emitting or absorbing. So sources or sinks of CO2 or methane in the natural ecosystem, forest, burn forest, river, peatlands. And then if we put the reservoir on the top of that, what will be the difference overall between before and after the creation? So that's what we tried to document. We did document at East Main. It's basically a large scientific study that was done by University of McGill and University of Quebec in Montreal. Many different students and experts working on that. As I mentioned before, 250,000 of measurements over 7 years. That includes 3 years before the flooding and 4 years after the creation of the reservoir. So you can see on the map here, this is East Main area, and we are actually doing the same thing with the Romaine complex. Romaine 2 net emission should be produced by the end of this year by University of Quebec, Montreal. So we'll keep you informed of that, but that should come later on this year. So what we do, it's measure the fluxes at the surface of East Main, and then subtract from that the emission, or add to those emissions of the reservoir, depending if it's source or sink, the emissions coming from the peatlands, the forest. Forest fire has a major role in the terrestrial ecosystem and boreal forest, as well as what's coming out of river and lakes. And then we try to look at what's going on over a period of 100 years for international standard. So basically, it's easier said than done. So in order to document the fluxes of those different pathways or terrestrial ecosystem, lakes, river, forest soils, we've used different technology, some which are on the top left corner, which are traditional chamber, clear or dark chamber, to determine respiration and photosynthesis of the vegetation. We use high frequency measurements, and the middle picture at the top for a covariance system. One station, but give you a lot of information on temporal variability. We use winter to our advantage in some area for some taking cores of sediment in the bottom of the reservoir or lakes. And so we use different techniques and technology to tackle the spatial and temporal variability. And we use all those technology and information together to get a mass balance of that. So what it means in terms of mass balance is, if you look here at the forest, it represents on the ground 340 square kilometers, or 53% of the future reservoir. This main one, it's about 600 square kilometers. So we've done all that calculation for the different habitat on the surface they occupy on the soil, on the ground, sorry, peatland, forest, and all the different aspects that have been considered. So another way to represent that, it's if you look at the green area to the left side of the picture, it's the captation of fixation sinks of carbon, of CO2 from the terrestrial system, which is something we were expecting. As forests to grow trees, you need to absorb CO2 from the atmosphere, or wetlands to basically accumulate peat. You need to absorb CO2 from the atmosphere. So you basically have sinks of CO2 in that area. On the contrary, on the opposite side, you have all aquatic ecosystem, which are the link between terrestrial ecosystem and the ocean. They're basically emitting CO2 to the atmosphere. And if you look at the surface they occupy on the ground, all of those different ecosystems we've been monitoring or measuring, you have a net sources of CO2 before flooding this main area. We do the same thing for methane. Even though here it's not a really big surprise. Wetlands are known for sources of methane. As the water table is high in wetlands, you have favorable conditions to produce methane. So we knew that from the beginning that natural ecosystem will be a net sources of methane, mainly because of the wetlands that they are present in the system. So looking at the net emission from reservoir for natural ecosystem, we know that contrary to what people think, in the case of different depending where you are, so you have to go case by case. In the case of East Main, the natural ecosystem were a source of CO2. Now we've done, it's look at the different pathways I've talked about earlier. It's a look at this diffusion at the surface, the bubbling, and the degassing. And I want to bring your attention to the bubbling. Those are really small number, 18 on the average. 1,000 here for degassing, but the most important aspects, as I mentioned it already, it's the diffusion at the surface of the reservoir. The first year here at East Main, it's 500,000 tons of CO2 equivalent. So if you do that mass balance year per year, so 2006, 7, 8, and 9 after flooding, and to a lesser extent, we've done also measurement 2010, 11, and 12. We've done measurement in 2018, but haven't put them on the graphics. And we were supposed to go back to this year, but because of this situation, we have postponed the sampling in next year. So we'll figure it out also next year. Where do we situate ourselves on the figure here? So this graphics includes all the net emissions already. So the area under the curve basically represents the quantity of greenhouse gases over a 100-year period that are above the natural ecosystem. So these are the emissions related to the creation of Eastman 1. So Eastman 1 basically produce more emission than the natural ecosystem that is replacing. So what we've learned from that synthesis, which is published in many papers, it's that the first emissions, the first years after flooding, we do have a large emission of greenhouse gases, as was known before, but now we have it also in the net emission. Rapidly comes back to natural values within a period of 5 years, in the case of East Main. The gassing are very small, and most importantly, it's that most of the gas is coming out of that reservoirs or Quebec reservoir or in a form of CO2. There's many reasons for that, but the most important reason why we have CO2 over methane, and that's basically what explains the difference between the reservoir in Quebec and reservoir in the warm area. It's that we have cold water and well oxygenated water. So if you take to the left side of the graphics, this is more tropical area. You have not much oxygen in the water. Water temperature is 20, 28. Chemistry 101, warm liquid will not hold a lot of gas, dissolved gas. So it's easy for the bacteria as they decompose organic matter to consume all the oxygen. And if you decompose organic matter and you have no oxygen, what's happening? It's basically favor the production of methane because there's no more oxygen to be used by bacterial activity. Because you in Quebec, we have, well, the opportunity or not, depending on how you see it, that we have a cold environment, cold water. We have oxygen the order of 8 to 9 milligrams per liter compared to 1 or 2 in tropical area. Have a lot of oxygen in the water, so so we will favor in terms of processes CO2 formation because there's oxygen available. Bacteria will favor that. It's much easier to produce CO2 than CO4, And if there's any CH4 produced at the bottom of the reservoir, the surface of interface water and sediment, that methane will be oxidized into CO2 or transformed into CO2 as it migrates in the water column because there is oxygen in the water. So the message is that we don't have conditions that favor the production of methane in Quebec. So fortunately for us, it's basically produce CO2 over methane. So basically, we have documented greenhouse gases in Quebec with more than 500,000, 500,000 greenhouse gas measurements, and we're still measuring that in many different reservoirs. It's been documented and published and reviewed scientific articles, so it's well known that the science, not just the measurements, but also the processes leading to those emissions. So we are able to compare what's going on in reservoir from Quebec with reservoir in Brazil or other areas because of that science that back up what we've been doing. So scientific presentation, many master and PhDs, and all that work was not done only by Hydro-Québec. It was done in collaboration with universities in Canada and US to figure out what we understand of the dynamic of greenhouse gases. So my home message here is we've documented in terms of science the fluxes as well as the processes, and then this information is passed through universities to calculate a life cycle analysis to be able to compare different sources of energy. That will be the talk of the next speaker. Ben?
Yes, Alain, thank you very much. What an impressive degree of data collection there. Must be a researcher's dream. Thank you. We'll get to questions for Alain at the end of the presentations. And next, I'm going to hand it over, if I can figure out how to do it, hand over presentation to Annie Levasseur. Annie Levasseur is a professor of environmental engineering at the École de technologie supérieure in Montreal. Her teaching is centered on integrating environmental and sustainability standards in engineering projects. After working for 8 years in the refining industry as a chemical engineer, she went on to earn a Ph.D. at the Polytechnique Montréal with a thesis presenting a new approach to dynamic life cycle assessments for global warming impacts. Research focused on climate change evaluation methodologies such as carbon footprints, life cycle assessments, and greenhouse gas emission inventories. Annie, we're delighted to have you with us. Thank you.
Good afternoon. I would just try to share the right screen. So where's my presentation? Has disappeared. Okay, I'm sorry.
No problem. Take your time. And to those of you who have asked questions, I'm receiving your questions and I will ask them in order at the end of the presentation.
So you can see my presentation, but it's not in full screen, isn't it?
That's correct.
Now you can see it in full screen.
Perfect. That's
okay. Good. Okay, thank you very much. So good afternoon. So as Alain said, the objective of my presentation today is to explain how we have developed the life cycle assessment values for electricity produced in Quebec. I say we, but in fact, I was not part of the team who performed the LCA study back a few years ago, but I'm currently working with Hydro-Québec on like integrating new emission from reservoirs into this LCA study, so I'm very familiar with it. And also I work a lot with the life cycle assessment methodology itself. So just a quick explanation of what is the LCA methodology for those who are less familiar with the idea. So the objective of any LCA study is to basically inventory all the resources that are extracted from the environment and all the emissions of pollutants that are released to the environment for any product system. So the methodology itself can be applied to any product, service, or project. And the idea is really to include everything that occurs throughout the entire life cycle. So for instance, for electricity, we want the construction of the power plants, the operation, and the end of life, and of course the use phase. So then when we inventory all these emissions and all these resources that are extracted from the environment, we then use different indicators in order to assess potential environmental impacts. So we want to translate these emissions into environmental impacts for different categories. So we hear a lot about climate change and what we call carbon footprint, and the result that I will show you will be the carbon footprint result. But we can, well, in fact, the LCA methodology usually presents results for other types also of environmental impacts. What has been done for the LCA of electricity in Quebec is to include, as I said, the construction of power plants and all the associated equipments, the buildings and the dams. We also have results for the electricity distributed in the province. So when we want the LCA of the electricity that is distributed, then we will add the construction of the transmission line, the substations, and the distribution network. So you see it here in gray instead of black, because in the results that I will show, we only look at electricity production. So we don't have this transmission and distribution, but we can add it. In terms of operation, we are going to include, of course, well, the reservoir emissions are occurring during the operation, but in fact, they are really caused by the construction itself of the dam and the power plant. We also include electricity losses, the consumables by the power plants, and or by also the transmission and distribution network when we include these phases. And then the end of life, in this LCA, the result that you will see, we don't have the end of life of the power plants. When they have performed this study, they have left it outside of the scope, basically because we didn't have any data about it, because all the power plants that have been built in Quebec since almost 100 years are still operating. So we don't really have data about this. So it's not part of it for the moment. The life cycle assessment has been performed, including all the emissions over a 100-year period, which is the international consensus about the lifetime of a hydropower plant. But we know that it can last longer than that, but it's really like a standard. So we used this period. We compare environmental impacts over the entire lifespan of the power plants. And you will see also that we compare the results obtained for hydroelectricity in the province to the results from other types of electricity production. These results are coming from the literature and from generic values. They are not specific to Quebec, as almost like 95% of the power that we produce is coming from hydro power plants. And the 7 indicators that we quantified, beside climate change, we also looked at ozone layer depletion potential, the acidification, eutrophication, the human toxicity, the smog potential, and resource depletion. For those of you who are interested, the full study is available using this link. Regarding the estimation of reservoir emissions, Alain just explained pretty well all the measurements that Hydro-Québec has done on different reservoirs. So right now, the data that we have contains like an average of all these emissions. And in the future, just if you are interested in this type of project, we are now working to update this data using a new model, which is called GRES. You can find the information about this model on the web. And this model has been created by researchers and also the International Hydropower Association in order to allow the estimation of reservoir emissions for any reservoir in the world, using a lot of parameters and data that they have collected, put all this together into a tool so that we can model reservoir emissions at any year following the creation of the reservoir, and also including pre-flood and post-flood emissions. So this is coming in a scientific publication, but it's not ready, so it's not yet part of the results that I will show. A very important aspect of LCA is that even if the life cycle lasts for 100 years, what we do basically is to aggregate all the emissions into one single value. So here on this graph, you see the dynamic of this 100 year. So at the beginning, of course, you have the construction activities. For hydropower, this is one of the main contributors, basically construction and the emissions from the reservoir. So the emission from the reservoirs, as Alain just told, are usually occurring in the first decades for boreal regions, as we have now, and they quickly decrease after. And you also have, of course, some activities regarding maintenance, rehabilitation, dismantling at the end, and some operation emissions also. Usually these emissions are less significant in the total emission of over the life cycle of the power plant. So this is an example of what we get when we inventory all these emissions. We have these different greenhouse gases, so CO2, methane, N2O. We also have CFCs and SFCs, for instance, which is used in some electrical equipment. So we have basically one single emission in kilograms or in gram for the per kilowatt hour, because basically we add all these emissions over the 100 year. We divide this by 100 years so that we get one emission per year, and then we divide it by the amount of electricity that is produced during 1 year to get emissions in gram of CO2 or gram of methane per kilowatt hour. Then what we get, usually what you see is the emission is expressed in gram CO2 equivalent per kilowatt hour. So the idea of going there is to aggregate all these different types of GHGs. So we use an indicator that allows us to put all this together by comparing the impact of these different gases on the atmosphere. So just to be a quick explanation. So the idea is to look at how GHG affect climate change. So let's say CO2 and methane, we are going to compare their contribution to radiative forcing, which is a way to measure the warming that they are going to have in the atmosphere. So if we compare, for instance, CO2 and methane, the most used indicator currently everywhere in the world is what we call the global warming potential for a period of 100 years. So what this means, when you see here that the value for methane is 30 from the last IPCC report, this means that methane over a period of 100 years following an emission will warm the climate 30 times more than CO2. So it's a relative indicator of the warming effect of methane compared with CO2 over a period of 100 years. So that's the indicator that has been used here. So basically, we multiply our emissions of all these GHGs by their indicator, their value of JWP 100 year, to get the carbon footprint. And that's how we arrive to one single value in gram of CO2 per kilowatt hour. So this is the results from this LCA study that has been performed and published in 2014. So you can see here on this graph that for the hydropower run of the river and hydropower reservoir, the results are really specific to the electricity produced in Quebec. So we have modeled the power plants and all the equipments that are in the province, so that we get a mix of run of the river and reservoir, and we have 6 and 17 gram of CO2 per kilowatt hour. And as I said early in my presentation, the other values for the other types of electricity production are values coming from the literature. So they are not specific to Quebec, as we don't have most of these, we don't have them currently in the network. So basically, we can say, looking at this figure, that the hydroelectricity in the province quite compares with other types of renewable sources of electricity in terms of carbon footprint. And of course, some of them you can see in the green boxes. They are the types of renewable, or well, nuclear is not really renewable, but it's quite low in carbon. They are a continuous output option, so that they are not intermittent as wind and photovoltaic are, for instance. Last thing that I would like to share with you is basically, as you saw, when we calculate the LCA of the electricity produced in Quebec, we aggregate everything into one single value. Of course, like in Quebec, we have more than 60 power plants. So these hydropower plants have been built, some of them almost 100 years ago. So here you have a very quick table of some of them with the commissioning date, just to give you an idea. Some of them are just have been put in operation just a few years ago, such as La Romaine, but others are quite old. So we know that these emissions are occurring at different moments over the years. So basically, we can see that, for instance, if we have a new power plant, some of the emissions are occurring right now and will be occurring in the future. But some of these power plants, the emissions, most of the GHG emissions that have occurred due to the construction and the first decades following the constructions for the reservoir emissions are from the past. So we can still operate these power plants. We still integrate their emissions into the carbon footprint, but some of these emissions have already occurred a few decades ago. So thank you very much for your attention, and I will be available to answer your questions.
Thank you very much, Annie. And we have been receiving a few questions, and I'll jump right in. The first is, we have heard claims of very high emissions of carbon from hydro reservoirs. Where do these come from?
Is it for me or Annie?
Go for it, Alain.
Okay, well, you have to understand that emission goes case by case. So 17 is the average for Quebec, as Annie mentioned. But so in Quebec, we'll have a variation between 0 to 30, 40, depending on the portion. Most of the emissions, or the high emission, comes from warm area. So it could be Malaysia, Brazil, or even in south of the US, where it's the temperature or high temperature or warmer than Quebec, with a lot of carbon in it. So it's certainly not an boreal system. You have some reservoirs which are higher than us in Finland or other places, but most of the high emission comes from warm area.
Okay. Annie, jump in at any time if you have anything to add.
Yes, of course.
The next question is, Alain has stated that emission levels return to natural levels after 5 years or so. Can he clarify natural levels? Is the comparison to a natural lake level, or is it to the prior as a forest level before flooding?
It will be about the same. What I mean by that, it's that the emission that we measure per surface area, the surface of a lake or river, will be the same in a reservoir after 5 or 10 years. That means that any natural aquatic ecosystem, lake, river, even a reservoir after 10 years, will have carbon going to the system by the runoff from the terrestrial ecosystem. So they do emit greenhouse gases, but it's not related to the flooded vegetation. So it's carbon coming from the watershed upstream of the reservoir. So it could be either the lakes around the reservoir or the river before the flooding. It's about the same order of magnitude in terms of emission after 10 years.
Okay, thank you. The next question is, the Natural Resources Council of Maine does not support the proposed Quebec hydro corridor through Maine. Do you know why, and what is your response to their criticisms? Thank you. I'll take a swing at that question.
Yeah.
It's really not my role to make the case for NRCM. They're more than capable of doing that for themselves, and for those who are interested in their arguments, they are well presented on their website, and I encourage you to look at those and review those. We are here to present the conclusions of the research by Alain and Annie's organizations that demonstrate that the source of this energy, when compared to other renewable sources, is relatively low in greenhouse gas emissions. And we'll be holding a companion webinar next week that with another representative from Hydro-Québec to talk about the delivery of this electricity into New England and the impact that can have on the reduction of greenhouse gas emissions from electricity generation in New England, mostly from our dominant fuel source, which is natural gas. So we're conducting a series of webinars that speak to what we think are the arguments in support of the project. And I'm happy to share with you the presentation by Bruce Phillips and John Herder at the end of March, the presentation from MIT a couple of weeks ago. We feel like we have a strong case to make that not only are there significant economic benefits to Maine and all of New England, but there's a net positive effect when it comes to reduction in greenhouse gas emissions. And that's what these presentations are designed to address. The next question, what are the mining and transport assumptions regarding thermal natural gas in life cycle analysis? I think that's you, Annie.
What of mining?
Mining and transport assumptions.
Okay, so like the percentage of the result that is attributed to this is, I don't know if it's the question. For instance, with fossil fuels, most of the time the emissions attributed to mining and refining, in the case of petroleum, with natural gas you don't really have refining, but all these upstream emissions, they can be like 10 to 20% of the total carbon footprint, and the operation phase, like burning the fuel itself, tends to be like something like 80% or 85% of the total carbon footprint. So basically, of course, the different ways we use the fuel, then we can have a variation between these proportions, but it's quite like a rule of thumb for the fossil fuels.
Thank you. Our next question is, does the life cycle analysis take into account changes in the carbon cycle due to the downstream effects of operations on changes to the flow regimes of floodplain forests, estuary deltas, etc.?
In the LC itself, no, we really account for the emissions from the reservoirs. Then, Alain, I don't know if you have something to say about how it affects emission downstream.
We take into account the downstream emissions. We can measure the emission as long as they go, but for sake of simplification, what we assume is that anything which is over the equilibrium saturation, so it's what, 432 in terms of ppm of CO2 in the atmosphere. So anything above 432 in the water, we assume it will be degassed, either right at the dam or downstream of the river. So that's taken into consideration in life cycle analysis by integrating the degassing for the aspects of greenhouse gases.
Thank you. Our next question, can a hydro project in Quebec quickly change its electrical production based on variations in wind and solar production in New England? Can Hydro-Quebec's reservoirs serve as our battery? And the question refers back to presentation from MIT a couple of weeks ago. Alain, I don't know if you feel equipped to respond to that.
Well, it's quite easy to start up a power station in Quebec. It's a couple of seconds, 20 seconds to start it up. So if there's a decrease in the demand or because the wind is going down, it's easy for us to start up the power and then export it to the US. Yes, this is something that we have the flexibility with hydropower. Yes, we do have that flexibility.
Thank you. We have somebody who wants to add to that. Gary Sutherland with Hydro-Québec. Gary will be our presenter next week, and it will speak to more of these issues. But Gary, you want to take a swing at that?
Definitely, Ben. Thank you for the opportunity. And we can maybe get into this a little bit more next week as well. But our system does have a possibility within minutes of ramping, we call it ramping up or ramping down in the electricity industry. But about 5,000 megawatts can be ramped up or ramped down in just a matter of minutes. So that is more than enough to be able to take into account some of those fluctuations that we may see on the grid at a later time. And if we think about the MIT study, that's exactly what they were getting at is what are those fluctuations that are going to be coming into line when there's a considerable amount of variable generation that's on the New England grid, and how will those be compensated? So we're quite confident that our system would be able to take those on. To give you an idea, today in Quebec, we have close to 4,000 megawatts of wind on our system operating, and it's entirely our hydropower that balances or backs up that wind, and does it quite successfully, seamlessly, and the end user doesn't know that there's been a fluctuation in the wind production whatsoever.
Thank you, Gary and Alain. And for anybody who is interested in more details about the MIT study that we're speaking of, we had researchers from MIT present here 2 weeks ago, and I have that presentation available on YouTube. I'm happy to send you a link. Just send me an email and I'll get that right out to you, as well as a link to a summary of their research. Our next question is for Gary and the others. Can you speak to Hydro-Québec's plans to add new turbines to existing reservoirs?
Sure, I can maybe take that. Right now, so we are still in a construction phase on our latest generation complex, which is the Romaine complex. It will be completed in 2021, the final generating station on that complex. We are actually in a situation right now where we have large surpluses of electricity on our system, so we don't currently have any plans to upgrade in the near future. There are a number of upgrades that can be done on our system, and that's something that we look at every time we are in kind of towards the end of the lifespan of a generating station, and we do need to make a refurbishment on that generating station. Of course, if you look at some of our stations, we do have some that are over 100 years old. So those are definitely cases where we look at what improvements we can make, and quite often those improvements are substantial. It means basically doing a little bit of machining techniques on the turbines, increasing their performance, quite often significantly, 4 or 5% in sometimes, because of course some of those stations were built at times when we didn't have the modeling techniques that we have today. So as we move forward, that is definitely part of our plan. It's not something that we're doing right now because we need the energy, however, because once more we're in a surplus.
So Gary, that's just, these are efficiencies to existing plants, so it's no new reservoir, no new flooding. It's just more efficient generation from an existing reservoir.
Exactly. So maybe to give you a more concrete example, our largest generating station, Robert Bourassa, which is in the Le Grand complex, is currently undergoing a major refurbishment. So it's 16 generating units. We take one generating unit out of its turbine pit every year and refurbish it. So it's quite a long program. It's going to be going on now for a few more years. And we do get increased performance out of that, which basically means that we are generating the same amount of energy, but using less water when we do that. But yes, as you said, Ben, no new no new creation of reservoirs. These are on existing facilities. And there's still a lot of maneuvering room to do that on our system across our 62 generating stations.
Thank you, Gary. And Annie, a question for you, my question, why do we have the 100-year standard?
Basically, because you mean for the lifetime of the power plant?
Yeah, the life cycle analysis. Why is 100 years the standard?
Yeah, for the power plant, it's because these they are lasting a very long time. So it's like natural to amortize the construction emissions over the entire lifetime of the power plant. So this is why we use 100 years for these. In fact, they might even last longer. So if we would do it, but when most of the time when we do the LCA, we don't know exactly when it will be at its end of life. So there's like a consensus that we are using 100 years in order to amortize.
Sorry, yeah. That's an international consensus on using the 100-year unit as a standard of comparison.
Yeah.
Yeah. Thank you. Next question is Hydro-Québec or are the potential contractors in New England considering ways to mitigate the short-term emission spikes from the new and under construction reservoirs supporting the excess capacity contracts? So my understanding is that this won't answer the entirety of the question, but that there are no new reservoirs being constructed to supply the contract for the New England Clean Energy Connect. Is that correct, Alain or Gary?
That is correct, Dan. There are no new generating stations that are necessary. So, and once again, we will get into this in a little bit more detail next week on the webinar. But Hydro-Québec has actually been undertaking a very large build out of its system for the past since 2003, so the past 17 years now. We have been increasing our generating capacity and bringing new facilities online. Now, of course, that had nothing to do at that time with NECEC. It's because there is a greater demand for clean energy throughout our export markets, and we wanted to make sure that we were in a position to be able to deliver some of that clean energy into those export markets. And because our facilities do take a long time to build, that's something that we had to do beforehand rather than later.
And speaking to the first part of the question, ways to mitigate the short-term emission spikes, it seems to me, judging by the conclusions from the conclusions reached by the Public Utilities Commission here in Maine, that the importation of up to 1,200 megawatts of hydroelectricity from Quebec would displace a significant amount of electricity generation here in New England, our dominant fuel source being natural gas. So there's sort of an inherent mitigation in this importation, exchanging natural gas production for lower carbon hydro production.
Yeah, exactly. Let's remember that about a little over half of the electricity generated in New England is generated from fossil fuel sources. So these new terawatt hours that will be arriving in New England, of course, are going to be displacing that fossil fuel source. And that's a much greater source of carbon emissions going up into the atmosphere than the initial carbon emissions that come off of our reservoirs. And if we look at our reservoir system, and maybe Alain can jump in with some of the ages of our reservoir systems, I believe that there's only perhaps one reservoir of Romaine that is in that initial period of slightly higher emissions that is present right after reservoir impoundment.
Yeah, it will be Romaine, but Romaine will have a small amount of greenhouse gases.
Yeah, it's a good point that Alain makes, because Romaine, because of the geography of the site, actually has a much lower carbon footprint than many of our facilities. And that's, really just because of the topology that it's been built in. So it's one of the ones that we can point to as being the most efficient from a carbon standpoint.
give you an idea that the average in Quebec, Annie showed it's 70 with the generating station with reservoirs. Ramen will be the other 5 to 10 the average.
So the next question, and we really have time for one or two more questions maybe. What are the expected changes to the Hydro-Québec systems with effects of climate change? I think that what that's asking is, will you have a water supply?
I can maybe give one indication on that one. Alain, would you like to go ahead, or?
Jerry.
So there is one study out there that we can point to, and we can provide listeners with the reference to that study that was done by a consortium that's in Montreal called Uranos that looks at questions of adaptation to climate change. So they do a lot of work on what is going to be happening in the next few decades and how, for example, the electricity sector has to adapt their facilities, and that can be anywhere from generation through to transmission and distribution to deal with that type of thing. And they have done one study on what hydrology or water inflow perspectives will be for Quebec in coming years. Because as we know, with climate change, there is a phenomenon where climate zones are moving further north. Their results right now show that we are likely to have about 14% more water in the mid-north to northern regions of Quebec. So that's where most of our reservoir generation is located, and probably about 5% more precipitation in the southern part of the province.
Excellent. Thank you.
Oh, and sorry, I should mention that study is, those numbers are 14% and 5% respectively between now and 2050.
Very good. Thank you. Well, I see now we're just past 5 o'clock. I want to thank our excellent presenters for sharing your research with us, really compelling information. And I want to thank all of our attendees. If we didn't answer your question completely, or if you have questions that we didn't get to, please email me. We're delighted to respond to your questions. Thank you all very much. And please plan to join us. I'll be sending out an invitation, hopefully in the next 24 hours, to the follow-up presentation. Gary will lead us through a discussion of the effects, the positive effects when it comes to greenhouse gas emissions by bringing this energy into New England. Again, thank you all very much and have a lovely evening.
You're welcome. Thank you.